A few questions came in on question 18 as well, where it asks you to match the orbital overlap for each indicated bond. And so to do that, we have to figure out the hybridization of each of these atoms. And so we're going to start all the way on the left and work our way across. So on the left, I have hydrogen. Hydrogen only has one orbital, the s orbital. So there is no hybridization. So hydrogen brings its s orbital. Now I'm going to look at this carbon. Carbon has two electron domains, 1, 2. With those two electron domains, I need two hybrid orbitals. I'm going to mix together an s orbital and a p orbital for sp hybridization. Right, so I'd have an s orbital overlapping with an sp orbital. So question 1 matches A. For bond B, it's asking for the sigma bond. Well, I know this carbon is sp hybridized because it has two electron domains. This carbon is also sp hybridized because it also has two electron domains. So the orbitals would be sp to sp. Bond C, well, I know carbon is sp hybridized. Now taking a look at nitrogen, nitrogen has 1, 2, 3 electron domains. 3 electron domains, I need 3 hybrid orbitals, right? So I'm blending together one s orbital with 2 p orbitals, sp2 hybridized. Choice bond D, the pi bond between nitrogen and oxygen. Well, I know nitrogen is sp hybridized, and this is where this one gets a little bit tricky. Because nitrogen is sp hybridized, right? Because it has 3 electron domains. Oxygen is also sp hybridized. And what that means is of my s orbitals and my p orbitals, right, I'm going to take one s orbital and 2 of my p orbitals. I take one s orbital, 2 p orbitals, blend those together, and then out of that, I'm going to get 3 orbitals that are sp2, and I have 1 orbital that's left over as an unhybridized p orbital. So now assign the electrons that I have, and I'm going to assign the 4 electrons to nitrogen, right? 1, 2, 3, and 4. And I'm going to assign the electrons I have to oxygen, which are 6, 1, 2, 3, 4, 5, and 6. So here would be my nitrogen-oxygen sigma bond between an sp2 and an sp2 hybrid orbital. For the pi bond, it would be between the p orbital and the p orbital on nitrogen and oxygen. So bond D would be a p to p orbital. Bond E, so we know nitrogen is sp2. Taking a look at the oxygen, oxygen has 4 electron domains. 1 is a bonding, 2 are bonding, and then 2 are non-bonding. Those lone pairs of electrons represent 2 domains. So 4 total domains makes it sp3 hybridized. We'll skip F for a second, and then we're going to go to G and H. So if I look at, I guess I have to answer sulfur. Sulfur is, right, 1, 2, 3, 4 electron domains. Because sulfur has 4 electron domains, it is sp3 hybridized. Carbon also has 4 electron domains, 1, 2, 3, and 4. It is sp3 hybridized. And then carbon is sp3. Hydrogen only has an s orbital, right, that I can bring to the table. So sp3 overlapping with an s orbital on hydrogen. Bond F is a little bit challenging because this is very similar to question 30 from the homework, where we have a pi bond between sulfur and oxygen. So again, we know oxygen is sp2 hybridized, which means it has an unhybridized p orbital that it's going to use for the pi bond, right? We can only use p orbitals or d orbitals to create our pi bonds. So we have one p orbital left over from oxygen, so part of this bond is going to be a p orbital from oxygen. If we take a look at the sulfur is sp3 hybridized, and that means it mixed together the s orbital and all 3 p orbitals. So it does not have a p orbital available to form the pi bond, and yet here is sulfur in 2 double bonds. So there are 2 pi bonds on sulfur. How does it do that? It uses an unhybridized d orbital. So I'm using the p orbital from oxygen, and I'm using one of the d orbitals from sulfur to make that pi bond. So a d orbital from sulfur is going to overlap with a p orbital from oxygen to form that pi bond in this case, much like question 30 from the homework. So hopefully that helps break down this molecule. This is something we should all be comfortable with, figuring out hybridization, figuring out electron domain geometry, molecular geometry, and figuring out the bond angles in all of these instances.